Ever wonder how those massive language models get trained? Like, how do they learn to write and code and answer all our questions?
It's like teaching a computer to write a novel, code a website, and answer your trickiest questions all at once.
Right. It takes a ton of data and a ton of computing power.
And that's what makes this paper we're looking at today so interesting.
It's called Dataset Decomposition, faster LLM training with variable sequence length curriculum.
From Apple researchers.
Sounds like they've found a way to train these AI models more efficiently.
Yeah, they're challenging the traditional way we think about LLM training.
Okay, I'm intrigued. So how do they propose to do that?
Well, typically data is fed to the model in fixed length chunks.
Okay.
But this paper argues that breaking data down by document length, like the original document length, can actually speed things up.
So instead of chopping everything up into the same size pieces, you group things by the document they came from,
Exactly.
and that makes things faster.
That's what they found. And not only faster, but it can also improve performance on language tasks, especially those that need more context.
Interesting.
Yeah, they highlight that in the abstract.
So the traditional method, they call it concat-and-chunk, right?
Mhm.
And they describe that in section 1. Taking documents of all different lengths, stitching them together, and then chopping them up into fixed length sequences.
Right. So you could have like a bit of a news article and then a recipe and then a poem all in the same sequence.
A total jumble.
And that leads to what they call cross-document attention.
Cross-document attention.
Yeah, it's where the model's trying to find relationships between parts of the sequence, but those parts are from completely different sources.
So it's like trying to follow a conversation where people just keep jumping in with random thoughts.
Exactly. And in section 2, they talk about how that's not only distracting, but also computationally wasteful.
Because the model's attention mechanism has to work overtime.
Exactly. Trying to figure out which parts of the sequence actually go together.
Which ties back to what they mentioned in the introduction about the quadratic cost of attention mechanism.
Right. The more the model has to jump around, the more computing power you need.
And they actually show this visually, right?
Yeah, in figure 2.
Figure 2 shows the concat-and-chunk approach versus their dataset decomposition method.
And you can see how much more organized the dataset decomposition looks.
Definitely. It's like those clear buckets of sequences.
And each bucket is all from the same document.
Ah.
So that's the core of their dataset decomposition method, or DD.
DD.
They describe it in section 2.1, sorting the training data into those buckets based on the original document length.
Instead of chopping everything up.
Right, you keep the documents together and group them by length.
So it's more like organizing your bookshelf by genre. Makes it easier to find what you're looking for.
Exactly, and by grouping those sequences from the same document, you eliminate that cross-document attention.
And they actually quantify that, don't they?
They do. In section 2.2, they say this approach reduces the number of tokens involved in cross-document attention by a factor of 8.
Wow, 8 times fewer. That's significant.
And it leads to some benefits, not only in training speed, but in the model's performance, too.
Right, and they show that in figure 3.
Figure 3 shows that models trained with DED actually perform better on tasks that require a longer context.
Because they can actually see those longer relationships within a document.
Exactly. They're not getting distracted by all that extra noise.
Makes sense. And they also mention in section 2.2 that this helps reduce spurious modeling.
Spurious modeling?
Yeah, where the model starts picking up on patterns that aren't actually meaningful.
Oh, right.
So by giving the model more coherent information, it's learning in a more accurate way.
Okay, so you've got these neatly organized buckets of data. How do you actually feed them to the model?
That's where variable sequence length training comes in, or VSL.
VSL.
They talk about that in section 2.3.
And what's VSL?
It lets you adjust the chunk size based on the bucket you're pulling from.
So you can speed through the shorter sequences.
Exactly. And then slow down for the longer, more complex ones.
Smart.
And figure 4 actually shows the time difference in processing shorter versus longer sequences.
So you can really see those time savings.
Yeah. In section 3.1, they quantify that. They show how much longer it takes to process sequences of length 8192 compared to length 64.
And that difference is significant.
Oh, yeah. For the OpenLM1B model, it's a 35% increase.
Okay.
And for the OpenLM3B model, it's an 88% increase.
Wow.
Even for the larger 7B model, there's a 23% increase.
So sticking to a fixed sequence length is a real bottleneck.
Especially as those models get bigger.
Makes sense.
Now, VSL doesn't just speed up training, it also allows for something called curriculum learning.
Curriculum learning.
That sounds interesting.
It is. Think about how we learn. We start with the basics, and then gradually work our way up to harder things.
Right.
That's the idea behind curriculum learning, and they explain it in section 2.4. So with DD, you can control the order the model sees those different sequence lengths in.
Exactly. You start with those easy short sequences and then slowly introduce the longer, more complex ones as the model gets better.
Like a personalized training program.
And they show the results of this in Table 2.
Table 2 shows how different curricula, so the order you present the data, can affect the model's performance on different tasks.
One example they highlight is the Grow P2 curriculum.
P2.
Yeah, where they gradually increase the probability of sampling from buckets with longer sequences.
So the model's slowly getting exposed to those longer chunks.
Exactly. And section 3.4, they mentioned this Grow P2 curriculum led to both better performance and the increased training stability.
So it's not just learning faster and more accurately, but it's learning in a more stable way.
Exactly.
That's impressive. Now, to really understand the impact of sequence length, they did an interesting experiment described in section 3.2.
Oh, what do they do?
They trained separate LLMs from scratch, but each using only one bucket from their dataset decomposition.
So one model was trained only on short sequences, another only on medium-length sequences, and so on.
Exactly. And then they tested how well each model did on different language tasks.
Interesting. So did the models trained on longer sequences just perform better across the board?
Not necessarily. In Figure 5a, they show how the performance varies depending on the task and the length of the sequences they were trained on.
Okay, so it's more complicated than that.
Right. For some tasks, like common sense reasoning, they actually found an inverted U-shaped relationship with the pre-training sequence length.
So there's a sweet spot, a certain sequence length that's best for those tasks.
Precisely. But for other tasks like reading comprehension, longer sequences were definitely better.
So it's not just about training on the longest sequences possible.
It's about finding the right balance. It depends on what you want the model to do.
I see. To really dig into this sequence length bias, they did another experiment.
Oh. Tell me about it.
It's also in section 3.2. They created two new buckets of data, both with sequences of the same length, but they came from buckets with different original sequence lengths.
Okay, so one bucket had chunks from longer documents that were broken down into shorter sequences.
Right, and the other bucket had short sequences that were stitched together to create longer ones.
So they could isolate the effects of sequence length and document content.
And did the content make a difference?
It did. The model trained on the bucket with chunks from longer documents performed better.
Even though the sequences were the same length as the other bucket.
Exactly, and they show this in Figure 5c.
So it's not just the length of the sequences that matters, it's also what's in them.
Exactly. Now in section 3.3, they look at what they call data mixture.
Data mixture, what's that?
It's the proportions of sequences from different buckets that are in the training data set.
So you could have a mixture that's mostly short sequences.
Right, or one that's balanced, or one that's mostly long sequences.
And they experimented with different mixtures.
Yeah, and what they found is, again, the optimal mix depends on the task.
Of course.
So if you need a broader understanding of the context, you'd want more long sequences.
Right. And they summarize the performance of different mixtures in Table 1.
Table 1.
And they also talk about the natural length distribution.
Natural length distribution.
That's the distribution of sequence lengths you get when you just use the buckets created by DD without doing anything special.
Okay.
And they found that this natural mixture actually did really well,
Interesting.
especially compared to the traditional method with a fixed sequence length.
So it seems like DD just naturally creates a good data mixture.
Now, how about scalability? That's got to be a big question for any machine learning technique.
It is. And they address that in section 3.5.
Does it scale well?
They did two sets of experiments, one focusing on dataset scaling and the other on model scaling.
Dataset scaling.
Yeah, they trained a model using different amounts of data and compared DD to the traditional method.
And did they need more data to get the same level of accuracy with DD?
It was actually the opposite. Figure 1a shows that DD consistently achieved the same accuracy as the traditional method, but with less data.
So it's more data efficient.
Exactly. And then they did those model scaling experiments where they tested DD with 3 different models.
Increasing in size and complexity.
Right. And Figure 1b shows DD led to better accuracy and faster training times for all 3 models.
Wow. So it works well even with larger, more complex models.
Exactly. That's really promising for the future of LLM development.
Okay, so it seems like DD is a real winner. But to be sure, They also tested it with a completely different data set.
Oh, right. They describe that in section 3.5 as well.
And those results are summarized in Table 3. They found the same thing. DD consistently outperformed the traditional method.
That's great. So it's not just a one-off solution. It seems to be a general approach.
Now, they didn't stop there. They also compared DD to other state-of-the-art techniques in Section 3.6.
That's good science.
They wanted to make sure DD wasn't just better than the traditional method, but better than the other best approaches out there.
So what did they compare it to?
3 other methods: document masking, best fit sequence packing, and in-context pretraining, which they call ICLM.
Okay, let's break those down. Starting with document masking. What's that?
It's basically what it sounds like. They mask out portions of the input sequence so the model can't see the tokens from unrelated documents.
Oh, interesting.
They explain that in detail in Section 3.6.1.
So it's like putting blinders on the model so it doesn't get distracted.
Exactly. And it does help improve performance on some tasks, but it also has some drawbacks.
Such as?
Well, it can hurt performance on tasks that need a wider context.
Right. If you're masking out too much information, the model might miss important connections.
Now, the second method they compared it to is best fit sequence packing.
Best fit sequence packing.
They describe it in Section 3.6.2. And in Appendix D, they give a more detailed explanation of their implementation.
Okay, so what's the basic idea there?
It's about arranging the document chunks as efficiently as possible within the sequences.
So you minimize the amount of chopping up you have to do.
Exactly. And it does lead to a higher average context length compared to the traditional method.
But is it better than DD?
Not quite. DD still does a better job of preserving those longer stretches of coherent text.
Okay. And they show that in Figure 3.
Mm-hmm.
Okay, and what about that third method? In-context pre-training, or ICLM?
Right, ICLM. They describe that in Section 3.6.3.
So how's that different?
Instead of grouping by length, you group documents by how similar their content is.
Oh, interesting. So you're putting similar topics together.
Exactly. And they found that ICLM does lead to improvements on some tasks.
Especially those that need a longer context.
Right. But it also has a big drawback.
Which
it's computationally very expensive.
Because you have to figure out how similar all the documents are.
Exactly. So it's not really practical for large-scale training.
So DDD seems to strike a good balance.
It is efficient and effective. And you don't need all those complex calculations.
And how did DD compare to these other methods overall?
Well, they summarize the key results in Table 5.
Table 5.
And DD actually outperforms all the other approaches on a variety of tasks.
It's really interesting that they compared their method to all these other techniques.
Now, in addition to the main paper, they also provide a lot of information in the appendices.
Oh, like what?
Well, Appendix B is full of details about their implementation and experimental setup.
That's important for transparency and reproducibility?
Exactly.
So other researchers can build on their work?
And they cover everything: the software and hardware they used, the specific hyperparameters, the curricula they tested.
They even provide specific details for each section of the paper.
Yeah, highlighting any deviations from the baseline hyperparameters.
Wow, Appendix B sounds like a gold mine.
And in Appendix C, they have some additional results that support their main findings.
Like what?
For example, in Section C.1, they break down how training time varies across different model sizes, sequence lengths, and batch sizes.
Okay, so a more granular look at those computational demands.
Exactly. And they present those results in Figure 7 as a series of heat maps.
Heat maps, those are always helpful.
And then in Section C.2, they dig deeper into the sequence length bias.
Oh, right. Trying to see if different hyperparameter settings could close that performance gap.
Exactly.
And did they?
Well, they found that even with those alternative settings, the model trained on shorter sequences still lagged behind.
So the sequence length itself really does matter.
They summarize those results in Table 12.
Table 12.
Now, in Section C.3, they give a more comprehensive view of those scaling experiments.
With detailed tables.
Yes. Table 13 focuses on dataset scaling.
What does it show?
It shows that DD consistently performs as well or better than the baseline, but with less data.
So again, it's more data efficient.
And Table 14 focuses on model scaling, and it highlights how DD outperforms the baseline in both accuracy and training time across all 3 model sizes.
That's great. Those tables really show the efficiency and scalability of DD.
And finally, Table 15 presents the results for the experiments on that alternative dataset.
The one from Section 3.5.
Right, breaking down performance across all those different tasks and benchmarks.
So consistent results across different data sets and training scenarios.
Exactly. Now, Appendix D goes deeper into that comparison with best fit sequence packing,
Okay.
and they provide a very detailed description of how they implemented that method.
That's helpful for anyone who wants to really understand the specifics.
They walk through all the steps involved in processing the refined web dataset and creating those training sequences.
Interesting.
And they point out that while best fit packing tries to minimize truncation, it doesn't eliminate it completely.
Right, you're still splitting up some documents,
And you can't guarantee that each sequence will be from a single document.
which is a key difference with DD.
Right. Appendix E looks at DD and training stability.
Training stability.
Yeah. Especially when you're training at large scale with big batch sizes and high learning rates.
It can be tricky to balance stability and efficiency.
Exactly. And they suggest that DD, when combined with a good curriculum, can help with that.
By gradually introducing those longer sequences.
Exactly. And to test that, they trained a model from scratch using both the baseline and DD with a specific curriculum called GROW P100.
GROW P100.
They actually use settings that usually make training unstable, like a high learning rate and no gradient clipping.
Bold move.
And they found that the model trained with DD was much more stable.
That's really interesting.
They show the training loss curves for both approaches in Figure 8.
Figure 8.
And you can really see the difference. DD leads to a much smoother, more stable training process.
So it seems like DD can help with stability, especially in those more challenging situations.
Now, Appendix F is an interesting one. They clarify the distinction between average sequence length and average context length.
Those terms can be confusing.
They're often used interchangeably, but there are important differences.
Right. So what are those differences?
Average sequence length is the average length of all the sequences in your dataset, or in a particular bucket.
Okay.
But average context length is the average length of all the possible contexts within a sequence. So considering all the subsequences that the model might use for prediction.
Ah, I see. So average context length is taking into account how the model actually processes the sequences.
Exactly. And they provide the formulas for calculating both.
And show how these concepts apply in different scenarios.
Right. It's important to make sure you're using the right term.
Definitely. Appendix F is a good reminder of that.
So we've covered a lot of ground. Dataset decomposition really seems like it could change how we train LLMs.
Yeah, it addresses a lot of the key challenges. Faster training, better performance, and even improved stability.
And the fact that it works across different datasets and model sizes is really promising.
It suggests DD could become a standard technique for training the next generation of LLMs.
I'm excited to see where this research goes.
Me too. It's fascinating to see these new approaches pushing the boundaries of what's possible with AI.
It really makes you wonder what the future holds.
It's a really helpful illustration to see the difference.
So Appendix F helps clear up any confusion about those two metrics.
Exactly. Now, they also talk about some of the limitations of traditional fixed-length sequence training in the related work section.
Oh, right. What are some of the key drawbacks they mention?
Well, one big one is that when you have a fixed sequence length, you often end up having to truncate longer documents.
To make them fit.
Right, and that can mean losing valuable context, especially for tasks that need the model to understand those long-range dependencies.
Like if you chop a document up into little pieces, you might miss the connections between those pieces.
Exactly. They also mention that fixed-length sequences can be inefficient for training, especially when you're using GPUs.
Because GPUs are designed for parallel processing.
Right. So if you have sequences of different lengths, the GPU has to wait for the longest one to finish before it can move on to the next batch.
So it's kind of like a group of runners where the fastest ones have to wait for the slowest one to catch up.
Yeah, that's a good analogy. Now, in contrast to those limitations, DD has several advantages. By using variable sequence lengths, it avoids that unnecessary truncation.
And allows the model to process those longer contexts.
Right. And by grouping sequences from the same document, you get those more coherent chunks of information.
So it's easier for the model to learn from.
Exactly. They also point out that DD is computationally efficient, especially compared to some other approaches that involve complex calculations.
Like that content similarity analysis we talked about earlier.
Right.
So it's faster, it performs better, and it's less computationally expensive.
Definitely. Wins all around.
Now, taking a step back, what are some of the key takeaways from this deep dive?
Well, I think it highlights that even in a field as advanced as AI, there's always room for improvement.
By questioning assumptions and trying new things.
Exactly. And it's a great example of how ideas from one field can be applied to another.
like that curriculum learning concept from education.
which has turned out to be really effective for training LLMs. I also think this research shows how important those design choices are when we're training these AI models.
Even something as seemingly simple as how we chunk the data can have a big impact.
On the model's performance and how it behaves, it's a good reminder to be thoughtful and deliberate in our approach to AI development.
Now, in their conclusion, the authors mention a few areas for future research.
Oh, what are they?
Well, they acknowledge that their work mainly focuses on the efficiency and effectiveness of DD.
Right.
But there are other important things to consider, like how well the model generalizes to new data.
Because just because a model does well on the training data doesn't mean it'll do well on data it's never seen before.
Exactly. So they suggest more research is needed on how DD affects generalization.
Makes sense.
They also point out that they focused on a specific type of LLM architecture, the transformer model.
Right.
So it would be interesting to see if DD works as well for other types of LLMs,
Definitely. And lastly, they mention combining DD with other techniques.
like content-based filtering.
Right, to further improve the quality of the training data.
So there's still a lot to explore. But DD definitely seems like a promising step forward.
It could be a big step towards developing even more powerful and capable AI systems.
Well, this has been a fascinating look at this cutting-edge research.
It's been great to discuss this with you. We've covered a lot.
From the technical details of DD to the bigger picture of what it means for AI.
Hopefully our listeners have a better understanding of how LLMs are trained now.
And how these new techniques are making that process faster, more efficient, and more effective.
As always, we encourage you to keep learning and stay curious.
And if you want to dive deeper into this research, we highly recommend checking out the full paper.
And the Open LM repository.
They have a ton of information and resources.
A wealth of knowledge for anyone interested in this field.
Well, that brings us to the end of this deep dive.
Thanks for joining us.
Yeah, it's really exciting to see how this research could shape the future of AI.
Definitely.
For our listeners who want to dig deeper, where can they find more information?
Well, the paper is publicly available. And the authors have made their code and data available too.
Oh, that's great. Where can they find that?
Through the Open LM repository.
Awesome. So other researchers can build on this work.
Exactly. And if anyone's new to LLMs, there are some great resources online.
They give a more general overview.
Yeah.
We can link to some of those in the show notes.
Definitely. Well, I think we've covered just about everything on dataset decomposition.
This has been a really in-depth look at this groundbreaking research.
It has. It's been a pleasure discussing this with you.
Likewise. And thanks to all our listeners for joining us on this journey into the cutting edge of AI. Until next time, keep those brains buzzing.